Hi, my name is Hilmeyer, and in this video I want to demonstrate our new functionality to import delay equations into MatCont, and that's the recent as of version 7.6. What is a delay equation? Well, a delay equation depends on the history. So here's an example on the screen. You see x depending on time, but on the right-hand side we see that we integrate over theta from -3 to -1, so it depends on the history. This is also a quadratic equation, so it's nonlinear. We see one parameter, gamma, and we will vary that later on. What I show in this video is that we specify the system, and then MatCont is a toolbox for numerical continuation and bifurcation analysis, which we will also see. And then we also added recently a method to compute Lyapunov exponents, and we demonstrate that as well. I've downloaded MatCont from SourceForge and unzipped that from my downloads folder, and then went into that folder where all these files are present. I typed MatCont to start it up. I already did so, but let's do it again. A new window appears, and that window is completely empty. It just means that we have no active system. So let's actually create that new system. Here is a delay equation importer. So we go from select, system, delay equation importer, and we create a new one. This window pops up, and it is a quadratic equation. So let's call it quad for quadratic to renewal equation. So RE. It has a coordinate x, a single one, and then there's a parameter gamma, and the equation is here. Let's have a look at the syntax. There's more info if you click on that button, but we can also read it off. The square brackets here indicating the dependence on time. There's the parameter gamma over 2 over here. This is the way we specify quadrature, so integration, and at theta, that means that's the variable of which we integrate, and here is then the integrand depending on theta and the domain from -3 to -1. 10, 10 are standard parameters for the approximation of the system. We press OK. All right. You see that MatCont has now an active system. We could do simulations, but let's go to the numerical continuation straight away. So I will look at an equilibrium. Why an equilibrium? Because 0 here is an equilibrium. Two windows appear, and I should specify one free parameter. Well, there is just one, so I click the radio button, and gamma is the active parameter. And now I would like to see the output. So let's monitor that. And we know a priori a bit about the range. So we'll go from 0 to 5 for the parameter gamma. I would like to see the state variable where the auxiliary variable here is okay. Let's go from -1 to 2. And then we start the continuation. All right, so we start at gamma 0. 0 is an equilibrium, and it just continues that, and it finds a branch point over here. When it finds a branch point, it stops, but we want to continue the continuation, and later on it finds a hop bifurcation. That hop bifurcation we ignore for a second. Let's take this branch point and start there. select that one. It's my new point and just compute it again. We have to stop. Okay, the system has now been imported, has been created. It's there, but nothing else is here over here. And we could do simulations, but we will not because we know a bit a priori, and I want to demonstrate the numerical continuation and the bifurcation analysis of this system. So let's go to an initial point and let's specify the equilibrium. And we know the equilibrium is at 0. And then we have one free parameter to specify, that's over here. So let's take gamma. And we want to see what happens. So we'll open a 2D plot. And let's see where we want to have a look. -1, 6 for gamma. And the ranges are changed. Let's compute forward. Okay, the continuation starts at 0 and then finds a branch point at gamma is 1. Very good. Let's continue. And then at gamma is 5, roughly, we find a secondary bifurcation, a Hopf point. Okay, nice. But that Hopf bifurcation is not too interesting, and we will ignore it. Let's take that branch point. By the way, the Lyapunov coefficient seems to be negative, so that's supercritical. Great. Stable oscillations are nice. But let's go to that branch point. We want to follow the other bit. And here we see a new part for x negative. And then we find a Hopf bifurcation over here. Press resume, stop, and have a look at the result. We look at the Hopf bifurcation. And also this one has a negative Lyapunov coefficient. Negative meaning that we expect stable oscillations to appear. Let's select this Hopf point and try to compute limit cycles from this point. All right, all settings are okay. Gamma and the period are active parameters. Let's zoom in a little bit and do compute forward. Okay, the continuation will start with finding a limit point at the Hopf point. We should ignore this point. The limit point of cycles. We should just ignore it. And then it takes a while. So I'm going to pause the recording for a second. So what we are looking at is the continuation of the limit cycle, and you see all the x variables for a fixed value of gamma. So here's the minimum, here's the maximum of this state variable, and we see that as gamma increases, the minimum and maximum change a bit. I think it's time to add something because this bifurcation is coming up. So let's add one thing. We'll add a numeric window because we want to see the multipliers. Let's arrange the system a bit. Why do we want to see the multipliers? Well, there's one over here that is becoming -1. So the modulus is 1, but the argument is 180. So this is -1, and it's going to find a period doubling bifurcation. This takes a while because it's also trying to compute the normal form coefficient of it and to see if it's sub or supercritical. And then once it has been found, we could continue this, but let's stop it for here. Let's have a look at the result, this period doubling, and it actually says negative. So here we expect a supercritical periodic 2-cycle. All right, that's nice, but now let's see what we can do with Lyapunov exponents. Compute Lyapunov exponents, we should change the type of the initial point. It's simply a point without special properties because we will do a simulation and compute Lyapunov exponents of that orbit. Should say that the type of curve that we look is not an orbit, not a simulation, but a simulation with Lyapunov exponents. So here's the Lyapunov exponent bit. And then we see a state variable, because we're now somewhere non-negative. This is fine. Let's keep it. There's some parameters over here. How often should we apply normalization, which is a necessary thing? Storage step. Should we follow the attractor? So restart from last state. That's good. Active parameter range. Yes, we will add that. We want to vary gamma of a range. So from 2.6, larger steps 0.2 till 3.4, from 3.5 to 4.3 in steps of 0.1, and then at the end in steps of 0.01. How long should the orbit be? Well, long enough. Let's take 2000 as an orbit. Init step size, max step size, in this case, do not really matter. And we press compute forward. And this is going to take a while. So long that it makes sense to pause this recording and resume later on. Hi, we continue. In the meantime, considerable time has passed because this computation actually takes a long time. It's not just a single exponent, there are many, and for many parameters. And you should not plot them in the meantime. It takes even longer. But now that the computation has finished, we have a look at them. So we open up a 2D plot, and we need to add some values. All right, I still want gamma to range from 2.6 to 4.6. And then I want to show Lyapunov exponents, and they're negative. So let's start first with -1, and I expect some chaos. So let's go to 0.5 and redraw the diagram. Oh, this is just the first exponent. We want to see all exponents. Okay, here they are. So here, over this range, all exponents are negative, and this is known for a steady state. Here, one exponent is 0, and that's characteristic of a periodic orbit or a limit cycle. The other ones are negative, indicating its stability. One exponent again touches 0, and then here is a additional bifurcation. This is actually the period doubling bifurcation. It goes down, reaches 0 again, And that's then a secondary period doubling bifurcation. And then at the very end, we see a positive exponent, and so you would expect some chaotic behavior over there. So we just saw that for gammas 4.6, we might actually expect some chaotic behavior because the Lyapunov exponent is positive, one of them. So let's do a simulation and see how chaotic it is. And for that, I'm not just showing the plot, but I'm also creating an event function. I'm creating an event function because we want to say that whenever the second auxiliary variable equals minus 0.2, that actually defines a section. We want to find many of those points, and we only want the positive crossings. You could change it to 0 or -1 if you want to. That's over here. And then we want to have a long interval. And now let's compute forward, and then MatCont will record this orbit together with the zeros of this event function. This takes a while. I'm not plotting this because plotting will mostly affect the graphical card, so that's slow. So we better have the computation run and then wait for it to finish. Yeah, forward 10 seconds. Forward another. No, anyway, it's finished. Good. I could inspect it this way, but actually I want to inspect it via a graphical plot. Why? Because I think we will see something in this system. So we will know that this 0 will be over here. So let's see that first. I plot this. Yeah, that's of course to be expected because it's at minus 0.2. So all the special points are over here. That's not too interesting. Let's do something else. So let's change the layout and actually look at the third one. And we want to change one thing. I had changed this to none so that only the special points are plotted. Let's plot it again. Okay, so this range does not seem correct. So after it has been plotted, we say fit range. Then also all of that will appear. Let's zoom in a bit on this, on all these intersection points. And in some sense, this is defines a one-dimensional return map. I'm sorry for all the labels of the event function. But what you see over here in that structure is something that is very typical of a horseshoe that we would also see in the Enol map for when it's chaotic So this then shows how event functions work, but then also how you then see some numerical evidence for chaos. And with that, I feel we've covered some of the new features of MatCont. Thank you for watching.